we want to talk about shear force and bending moment. So we've defined shear force already. We have also defined bending moment. So bending moment is the force that tries to make something to bend, while shear force is the force that tries to keep something from sliding. Okay, so that is the shear force and then the bending moment. So we have to draw the shear force and bending moment. So to get the shear force and bending moment, we first of all look at something very important. So we have upward reactions and then downward reactions. Very important, you must take note that we have just up and down, no left and right. So it's just up and down forces that are acting on this body. So we said summation of all vertical forces is equal to 0. Remember, when we talk about up and down forces, we're looking at what vertical forces. So summation of all vertical forces is equal to 0. So for this calculation, we will take upward forces as positive and then downward forces as negative. Upward forces as positive and downward forces as negative. Okay, so look at this very well. Then you see a beam here, sorry, a load, a distributed load here, and then we have point loads at several ends of the beam. So here is 1 kilonewton. Okay, so what the first thing we need to do, remember we said summation of all forces, all vertical forces equal to 0. Right, the vertical force we have ROB, reaction at B is one of the forces plus. We also have reaction at what? A, reaction at A. So remember, we must also take note that sum of upward forces is equal to sum of downward forces. For summation to be equal to 0, for the sum of all the forces to be equal to 0, it means that the upward forces must equal the downward forces. So if the upward forces equal the downward forces, if you move this other one to the other side, basically you have what? 0 as your answer. Okay, now then ROB plus ROA is equal to, so let's take the downward forces now. So the downward force we have 4 kilonewton plus we have 2 kilonewton per meter. So we change this distributed load. So this load acts along this particular lane. So it acts from here to here. So I'll change this to a point load. So if I change it to a point load, I'm going to have 2 times 2. And 2 times 2 is what? 4. So we have 4 kilonewton, right? Plus, then for this other one, we have 1 kilonewton plus 1. So that will give us 4 plus 4 is 8 plus 1 is 9 kilonewton. So 9 kilonewton is all the downward forces acting on this beam. So all the downward forces acting on the beam is 9 kilonewton. Now, what do you want to look for? We want to find the reaction at B and then the reaction at A as well. So we've gotten this already as ROB plus ROA is equal to 9 kilonewton. So now, to find the reaction at A, what are we going to do? So remember, we have moments. Moment basically is the turning effect of a body. So basically, we are going to take moments about point A. And moments about point A, we have clockwise movement and then anti-clockwise. So if a body turns, this beam can turn, right? So if I turn this beam, it can move clockwise or anti-clockwise. It can move like a clock, it can move against the movement of the clock. So I want to find the moments of that beam. So remember we talk about bending moments. Moment, we talk about something to bend. Okay, bending moments. Turning, that's what moments means. So summation of moments about A we say we equal to 0. Clockwise and anti-clockwise. So it must balance themselves for the body to be at equilibrium. So you remember that upward force is positive, then downward force is what? Negative. Okay, so now what are we going to do? Remember that moment is equal to force times distance. Force times distance. So that's one thing we should put in mind. So if I put that thing in mind and I'm taking the moment about point A, that means I'll start from here to take the moments. I have so I have the force RB is upward force, so it's positive, times the distance covered. The distance is here is 1 plus 1 2 plus 2 4 plus 1 5 plus 1 6 times 6. Okay, so minus. We're using minus because this is a downward force. So remember we say downward force is what? Minus. Okay, so we have the downward force of what? 4 kilonewton. That's the force times distance. Distance covered from here to here. We have 1, 2, 3, 4, and then 5. 4 times 5. Then we have this. I'll change this to a point load. So changing this to a point load means I'm going to have 2 kilonewton per meter times distance is what? 2 meters. So this meter cancels this meter, it becomes 4 kilonewton. So this 4 kilonewton is going to act at the center here at a point load. So if you act at the center, here is 2 meters. So it's going to act at the center, and then going to have here become from here to here is 1. So 1, 2, 3. So you're going to do what? Minus 4 times 3. Okay. So then I have what again? I have this final load here. So it's 1 kilonewton minus 1 times, that's as a span of what? 1 times 1 equal to 0. Okay, so the next thing to do, we have 6 times RB, 6 RB minus 4 times 5 is 20 minus 4 times 3 is 12 minus 1. So I have 6 RB equal to 0. So 6 RB is equal to 20 and 12 is 32. 32 and 1 equals 33. So it's equal to 33. So what do we do? So what do? We have RB is equal to 33 divided by 6. And that will give us what? 5.5 or 5.5. So 6 going to 30 is 5. Remember 3. So add 0 to that 3. So that becomes 30, right? So 5.5 kilonewton. That's the answer. Okay, so that is it. So we found RB. The next thing to find is what? RA. So remember that RB plus RA is equal to 9 kilonewton. So from here, remember sum of upward forces is equal to sum of what? Downward forces. So the downward forces we have is what? 9 kilonewton. So we have 5.5 plus reaction at A, which we are looking for, equal to 9 kilonewton. So from here, my RA, reaction at A is 9 minus 5.5, which is equal to, so 9 minus 5 is 4. So we have 3.5. So 3.5 plus 5.5 gives us what? 9 kilonewton. So if you take it to the right side, you have 9 minus 9, which is what? 0. Okay, so that's basically how to find the reaction at B and the reaction at what? A. So with this information, I can now find the shear force. So, alright, shear force at B is the same thing as the reaction at B. So reaction at B is what? 5.5 kilonewton. is equal to reaction at B, which is equal to 5.5 kilonewton. Remember, we're looking at force, right? So reaction at B is the same thing as shear force at what? B. Okay. So the next thing, we find shear force at point F. Shear force at F. So we have this 5.5. Then we are subtracting, we are going to be subtracting the forces. That's what we are going to be doing. So 5.5 minus 4, which is equal to 1.5 kilonewton. So that's basically how we find the shear force. So to find the shear force, I'm moving from this side, coming over to this side, I'll be subtracting the forces till I get to this point. And at this point, I'm supposed to get what? If I sum this guy and this guy, I should get what? 0. I should get 0. Okay, so shear force at F is equal to 1.5 kilonewton. So shear force at E will be the same thing. It will be same. There's no load here. There's no load here. So shear force at E will be equal to shear force at F, which is 1.5 kilonewton. So the same force that acts at this distance, the same force that acts this distance, right? Okay, so same force that acts at this point, same force that is acting at this point, because there's no load, no other load is applied here, just this load. Okay, now shear force at D, shear force at D will be equal to, shear force at D will be equal to, so remember we are subtracting, so we have 5.5 minus 4, 5.5 minus 4, minus, so we have minus 2.5 kilonewton. So that is 5.5. Shear force at D will be 5.5 minus 4 minus 5.5 minus 4 minus 4. 2 times 2, 4 minus 4, right? That will give us shear force at D, which is minus 2.5 kilonewton. Then shear force at C will be 5.5 minus 4 minus 4 minus 1 kilonewton. That will be minus 3.5 kilonewton. Alright. So shear force at A will now be reaction at A. So reaction at A, we got it at what? 3.5 kilonewton. So that's pretty clear, right? So the shear force at A will be equal to 0. So minus 3.5, that will be equal to 0. Shear force at A, let's do that. 5.5 minus 4 minus 4 minus 1 plus 3.5 equal to 0 kilonewton. We use plus 3.5 because that's upward force is plus 3.5. Okay. Bending moments. The bending moments. Let's look at the bending moments. So remember, we are looking at bending moments, and then we say that for moment is equal to force times distance. Force times distance. So if moment is force times distance, so we said the bending moment at B will be, take note that the bending moment at each ending is equal to 0. So bending moment at B and bending moment at A is equal to 0 kilonewton meter. So now bending moment at F will be equal to bending moment at point F. So the distance is from here to here. So we have 5.5 which is the force, right? And distance is 1 meter. So we have 5.5 kilonewton meter. So bending moment at point E, bending moment at point E should be the force is what? So we have bending moment at point E. Bending moment at point E should be 5.5 times the distance is 2 minus 4 times 1. So we have 5.5 times 2, that should be 11. 11 minus 4, that should be 7. 7 kilonewton meter. Okay. So bending moment at point, we've taken F, we've taken E, so we are taking D now. Bending moment at point D will be 5.5 times distance from here to here should be around 4 times 4 meter minus, this is 4, right? 4 times 3 meter minus, this is, you change this to a point loop. You change that to a point loop, you have 4. That is 2 times 2, that will give us 4. And then remember, it acts as the center of this. So from there to there, it was 1. 4 times 1. So 5.5 times 4 minus 12. 5.5 times 2 is 11. So 11 plus 11, that's 22. 22 minus 4, that's 18. Sorry, minus 12 is 22 minus 12, that's 10. Then 10 minus 4. 10 minus 4, that's 6. 6 kilonewton meter. So we have 6 kilonewton meter as the bending moment at point what? D. So bending moment at point E, at point C, sorry, will now be, we have 5.5 times, where is point C? This point C here. This point C here. So we have 5.5 times, we have 1, 2, 4, 5 times 5 minus 4. 4 times 1, 2, 4 times 4 minus, we have change this to a point loop. If I change this to a point loop, I'm going to have 4 times to add the midspan, the center. So from this point to this point should be 2, right? Because this is 1 meter, and then from here to here at the midpoint, which is going to act, that should be 2 meters. So times 2. So is equal to, so 5.5 times 5, you know, we have 22. 22 times 5 plus 5.5, that should be 27.5 minus, this is 16, this should be 11.5. 11.5 minus 8. So 11 minus 8 should give us 3.5. So we have 3.5 kilonewton meter. Alright, so this is a basic calculation we need to know. The basic things we need to know about this. So we've gotten all the points and they want to plot them here. So we want to plot them here. Okay. So we'll draw our line. So at point B, the shear force is what? 5.5. So that means I'm going to move up to a point, I'll call that point 5.5 kilonewton. Okay, so, and then there's no load here. So where there's no load, so no load, a straight line. a load, then we'll put what? Inclined line. So we have this as 5.5 and there's no load here, right? So I'm going to move straight. Okay. So I don't have a ruler. Okay. For the next thing, at this other part, there's a load here, 4 kilonewton. And then at that point, we said it went down towards 1.5 kilonewton. 1.5 kilonewton. It should be somewhere here. And then that's at point F, right? Point F we have 1.5 kilonewton. And then at point E, so the effect of this load, at point E we have, it's the same thing, the same 1.5 kilonewton, right? At point E. So we just move it this way. 1.5 kilonewton. So it maintains that particular load, right? That particular effect for this duration. So the next one, at point D, we see minus 2.5 kilonewton, minus 2.5 kilonewton, an inclined line. So minus should be around this way. So move it down this way to this point. So minus 2.5 kilonewton. Okay. So we now had minus 3.5 kilonewton. So you move down to minus 3.5 kilonewton. So move down to minus 3.5. So at this point you have minus 2.5 kilonewton, right? So that's at point what? At point D, right? So it maintained the same to point C. Maintained it to point C. And then at point C, we now had minus 3.5 kilonewton. So move down, minus 3.5 kilonewton. And then at that point, at point C, then it maintained it up towards point A. Maintained it up to point A. Maintained it up to point A. So at point A, we still have a minus 3.5 kilonewton. Remember now, the reaction at A is what? A 3.5 kilonewton. So if I add 3.5 to this, we're going to have 0. So it now went back to what? 0. Going back to 0. 0 kilonewton. So that's basically the bending moment, the shear force diagram. So what do I do? I'll just shape this point. I'll shape this point. And this point. So this point is negative. Here is what is positive. Okay. So now let's draw the bending moment diagram. Let's draw the bending moment diagram. Okay. So I believe this is clear. Remember, we had to draw a straight line here. Then we had an inclined line, basically because of this distributed load here. That was gave us this inclined line here. Okay. Alright, so for the bending moment diagram, let's have it here. So we have this point at 0, then 0, 2. Okay. So we have bending moment at B is 0, so it's 0, and then bending moment at F is 5.5. So bending moment at F is 5.5. So bending moment at F is 5.5. So when you have it as an inclined line, so yes, 5.5 kilonewton meter. Okay. So we have another one. Bending moment at E is 7 kilonewton meter. Is 7 kilonewton meter. So we have 7 kilonewton meter to end up again. 7 kilonewton meter. So we have bending moment at E at that. Bending moment at D should be 6 kilonewton meter. So because of this, we're going to have a parabola. Here is 6 kilonewton. Okay, so the bending moment at point C. Bending moment at point C should be 3.5 kilonewton meter. 3.5 kilonewton meter. And then it went back to 0. Okay, so basically you see that the bending moment is was positive. It's positive. So that is that. Remember we said for every straight line in the shear force diagram, we use it as an inclined line in the bending moment diagram, and every inclined line in the shear force diagram, we use it as a curved line in the bending moments diagram. So just take note of that. So you can share this point. Alright. So believe this helps. Thank you very much. You can like, share, subscribe.